Now let's move into our trigonal, bipyramidal, and our octahedral geometries. So these geometries can only exist because our elements in period 3 and beyond have those empty d orbitals that we can utilize when we are bonding. Because to get a trigonal bipyramidal geometry, we need to be able to have 5 electron groups around our central atom. And for octahedral, we need 6 electron groups around our central atom. So the only way for that to work is if we expand that octet. All right, so let's take a look first at our trigonal bipyramidal. Okay, so trigonal bipyramidal, this is probably the most complicated of all of the geometries. So this is what a trigonal bipyramidal molecule looks like. So the big thing to remember here, and this is going to be new, is that we're going to have 2 different types of zones. We're going to have an axial zone and we're going to have an equatorial zone. And these zones are really important. So there's 5 groups around trigonal bipyramidal. Our axial zone is going to have 2 groups and will always be bonding. Our equatorial zone can fit 3 groups. And our equatorial zone is where we can replace bonding groups with lone pairs. But it's really important, get this, start thinking about this in your head now, that the axial zone is always bonding. Lone pairs are only going to show up around the equatorial zone, okay? And so 5 electron groups. So my AX5, I have 5 plus 0. That gives me 5. AX4E, I have 4 bonding and 1 lone pair. 4 plus 1 is 5. X3E2, 3 bonding, 2 lone pairs, still 5. And X2E3 is 2 bonding, 3 lone pairs, which is also still, coincidentally enough, 5, okay? And we stop there. So even though, we're looking at this here, we can't tweak this around anymore. First of all, once we get down to there, we only have 3 atoms bonded together. But we're only dealing with electron groups on that equatorial region, okay? So let's start off, as usual, where everything is bonding. Okay, so our start off here, we have, again, 5 plus 0 gives us 5. All right, so we've got a central atom and 5 surrounding atoms. So we have 6 atoms, no lone pairs. Okay? All right, now when we look at our orbital and our molecular geometries, everything's bonding, so they're the same. So this is orbital, and this is molecular. Okay, and again, it's trigonal bipyramidal because I have 1, 2, 3 things around the equatorial region. And so it's like a pyramid, 3-pronged pyramid that points up and a 3-pronged pyramid that points down. So trigonal for 3, bi for 2, and pyramidal because it's like 2 3-pronged pyramids stacked on top of each other. Okay, so now we need to think about our bond angles. Okay, so our bond angles. Let's look. So I have circled in green. These are axial. Okay. And circled in purple. Okay. These are okay. So when I am, and I just realized I spelled angle wrong. I'm human too. All right. So anyway, we have our axial and our equatorial regions. So we've got 2 different bond angles going on. We're going to have a bond angle that's going from our axial to our equatorial, and a bond angle that's going around our equatorial atoms. Okay, so that axial to equatorial is going to be a 90-degree bond angle. Okay, so our bond angles. Okay, and then our equatorial is at 120 degrees, just like our trigonal planar was. Okay, so axial to equatorial, 90 degrees. And then around our equatorial region, that's 120 degrees. Okay, all right, so some examples. Okay, and again, the only way we can get this geometry is if our central atom is in something from period 3 and below. So that last example I put on there, the SOF4, can the oxygen be the central atom? No, it can't. The sulfur has to be the central atom because oxygen's in period 2. So in period 2, we have an N value of 2, all right? Which means we only have L values of 0 and 1. We only have S and P orbitals. But sulfur's in period 3, where we have an N value of 3. So we have L values of 0, 1, and 2, which means at an L value of 2, we have d orbitals. So our d orbitals do show up. They're unoccupied, they're empty, but they're there, which means we can use them. All right? So when you're thinking about how to draw these, got to break it down logically. Okay? I'll do the first one. I'll do the phosphorus pentafluoride here. Okay, so again, I've got my sigma bonds between everything. Okay, all right. And this is it. Just a phosphorus with 5 fluorines, all bound on single bonds there with the lone pairs around the fluorines. Okay. And so geometrically, here's what this looks like. There's that trigonal bipyramid with the 2 pyramids that are stacked on top of each other, and our equatorial and our axial. So again, you know, looking at this, there's that side view, and then here is that top view. All right. So for those of you joining us from the random reaches of the internet, if you do not have a molecular model kit and you're having a really hard time visualizing this, invest in a molecular model kit. You will thank yourself later. Those of you that are joining us from one of my courses, we do a lab where you will build all of this stuff with a molecular model kit. So we do provide those in our laboratory for you to build and manipulate in front of you. All right. But if you don't have a kit, or you know, regardless if you're one of my students or not, if this is hard for you to visualize, get a model kit. I'm going to give full disclaimer here. 3D visualization has never been my personal strongest suit. As I went through more chemistry, I mean, I had a model kit for lower levels, and it was definitely useful in organic chem, building some of the crazier stuff, especially when we started dealing with chair and boat forms of our benzene rings. So if you have to take OChem, chair and boat form, it's coming. So, you know, super helpful for that. But personally for me, like when I got into even higher levels and I started taking things like inorganic chemistry, and I had to learn things called point groups, which required rotation and symmetry, without manipulating something physically, I did have a hard time visualizing that. And I remember a very memorable day where my PI, I was doing undergrad research, so I was in a lab even as an undergrad, and my PI, Dr. Diane Smith, one of the most wonderful people I have ever known in my entire life. She noticed I was struggling with the point groups, and she pulls out her old model kit that she had stashed in the lab, and she hands me, and this is a more robust kit than I owned. I owned the standard kit for like general chemistry and organic chemistry, and my kit did not include pieces that would let me do the 5 or the 6 coordinate geometries. So she hands me her old model kit with all the pieces in it. And she says, all right, you're off research duty until you figure this out. So what ensued was literally 2.5 days where I did nothing but sit at a desk in the research lab, building, rotating, and understanding all the visualizations of these. So trust me, if you're struggling visualizing all the geometry, you are not alone, and it's okay, but get a model kit because it could potentially save your life, I guess, or your grade. All right, so model kits, highly, highly recommend them. Because this is where we start to get crazier. Like up to tetrahedral, it's not so bad, but now we're getting kind of crazy, especially with this axial and equatorial thing. Okay, so anyway, you know, when we start looking at this too, when we draw a Lewis structure, all right, you may remember in prep chem that you had to draw like a 3D representation of things where we had these wedges and dashes. I didn't showcase that in the first video with our linear, our trigonal planar, and our tetrahedral geometries because I trust that that was something that you covered previously. But I'm going to go into that a little bit now because, you know, here's, you know, a picture that's been a little bit better 3D modeled. All right, you can see, you know, like I have here, where we've got this, this, and this all in the plane of our central atom. But then I've got something sticking out one way and something sticking back the other way. And, you know, the previous one I drew just kind of everything arranged around that central atom was flat on the plane, was perfect for the Lewis structure. But when we start to think about what does this look like in three-dimensional space, how does it occupy that three-dimensional space, we have to visualize it a little bit differently. And so here I'm going to do a fluorine pentachloride, which that's the one that I have here. This is a really interesting molecule because fluorine typically doesn't like being a central, or not fluorine, sorry, I actually wrote something down now. Phosphorus pentachloride. You can't get fluorine as a central atom. It doesn't like being a central atom. I'm not sure what was on my paper there. Phosphorus pentachloride. 1, fluorine's not even in period 3, and 2, fluorine's always the surrounding atom because it's the most electronegative element on the periodic table. Sometimes it pays to be able to read your own handwriting. Don't write your notes quickly. Okay, all right, so phosphorus pentachloride. So I'm going to draw my phosphorus, and then in the plane, I'm going to take my chlorine, and my chlorine. So that's all part of the plane. And then if you recall, the way we represent 3 dimensions, I'm going to take a filled in wedge that gets bigger as it comes out, as though it's coming toward me. And I'm going to do a dashed wedge, getting smaller, as though it's going back behind. And so this gives us a kind of a 3-dimensional look at what this looks like in 3-dimensional space. Okay, this isn't a Lewis structure. We could, you know, be a little bit more exact. If we're not drawing a Lewis structure, we don't have to put the lone pairs on the surrounding atoms. But I'm going to go ahead and fill them all in on here. And so it takes, you know, something like this. And again, this is a perfectly fine Lewis structure. I wouldn't expect anything different unless I was asking for a 3D representation. But here's a, you know, a way you can visualize on a flat piece of paper, you know, what it looks like in that 3-dimensional space region. Because this is definitely not flat and definitely not star-shaped. Okay? All right. So now let's go ahead and start replacing some things with lone pairs. Okay, so before I take this apart and add a lone pair, I want you to study the two pictures I have up in this upper right region, and then look at my space filling model in the lower left corner. See if you can predict where I'm going to remove, and based on what I said earlier too, where do those electrons sit? Am I going to remove it from here, down here, or somewhere around the center? I'm going to move it from around the center, okay? Because again, the lone pairs have to sit on that equatorial region, and we'll discuss why in a moment here, all right? So we get this. Now I've got a lone pair there hanging out and floating around on my equatorial region. Okay, so in this case, I still have 4. Whoa, that was weird. I'm going to have to use the slide because unfortunately, the way this records, it doesn't let me go back. So I'm going to do 4 plus 1 gives us 5. So what I'm going to do is I'm going to write out what I was going to write out on the previous slide. And then I'll erase it and mark up this slide. Okay. So we're going to have 5 total atoms and 1 lone pair. Okay. And so if you saw the pictures I had on the other side, okay, what we have is we have orbital geometry. That's still our trigonal bipyramidal. But now our molecular geometry, or the shape of our molecule, is what we call seesaw. Okay, so why do we call this seesaw? So here's my equator. I'm going to turn it on its end like this. Okay, I don't know how many of you remember going to a playground as a kid that had a teeter-totter. Well, teeter-totters are also called seesaws. And so if I balance this on my hand like this, oh look, it goes like the teeter-totter, or the seesaw does. So that's why we call it seesaw. Okay, the molecular geometry, or the shapes, are all based on like a visual shape that we can represent. All right, and so what happens here with our bond angles is that our equatorial still is 120, okay? Because what's happening here, and this is why it has to be equatorial, is if you look at the picture here where it says axial lone pair does not occur. Because if we were to get something axial, all right, it would push down on all 3 things on the equator. Well, we still have another axial atom down here that's in the way. So first of all, it's trying to push out 3 things, get 3 things out of its way. And those 3 things are going to be coming up on what's already at the equator, taking up space. If the lone pair occupies an equatorial region, all it's going to do is it's going to squish these guys. Sometimes we might see some squishing of this, but typically speaking, that lone pair is really mostly going to affect what's happening between the equator and the axial, okay? So our axial to equatorial bond angle now is going to be less than 90 degrees, okay? So some examples. Actually, I may not need to erase everything if I do this smartly. Okay, so we'll do that sulfur tetrafluoride. Okay, so first I'm going to draw a Lewis structure, and then we'll do a 3D representation so that we can visualize this 3D model I have on our paper. So we'll do it all on the same slide. This will work. Okay, so all right. So then we're getting our lone pairs. Okay, so there is our Lewis structure. So now if I wanted to represent this in a 3-dimensional space like we have here, now I'm going to go ahead, even though they show the lone pair on the left side, I'm going to show the lone pair on the right side. For some reason, whenever I can, I always like to do my wedges and dashes to the left, I think just because that's the way I've done it forever. But anyway, there's my lone pair in the plane. And there's one sticking out and the one sticking back behind. Okay, so this lets us put a 3-dimensional model on our paper here. Okay, All right. So now, again, the only thing we can do as we add more lone pairs and get rid of bonding is add them equatorially. Okay. So now I'm going to get that. All right. Which takes us to this one right here. So we have 3 bonding, 2 lone pairs, still equals 5. All right, so now what do we have left? We have 4 atoms. We have a central and 3 bonding. Okay. So what happened here? Well, now we still have that trigonal bipyramidal orbital geometry. Because again, we still have those 5 things. And now our molecular geometry, or our shape, is T-shaped. So just like that seesaw, this is one where to really see the T, you got to turn it on its end. All right, so there's our T. Our bond angle. Well, now that my equator has been replaced by 2 lone pairs, I don't have an equatorial bond angle anymore. All I have now is just axial to equatorial. The lone pairs do squish that in a little bit usually. So we're going to say our bond angle we're just doing axial to equatorial. I'm going to abbreviate with EQ. And we're going to get that less than 90. Okay, so remember, we only have that 1 atom left equatorially, so we don't have a bond angle there anymore. And again, the reason why all the lone pairs are happening equatorially is because we're trying to minimize repulsions. And axial lone pairs would increase repulsions. Okay? All right, so examples here. Okay. All right. You can sort of draw this one looking like a T without worrying about the wedges and the dashes. But let's take a look and let's do a wedge and a dash drawing anyway. Okay, and so again, that molecular geometry is T-shaped because if you turn it on the other side. And so the way we can do this, all right, I'm going to show the fluorine here, the fluorine here, and the fluorine here. And then I'm going to show this lone pair and this lone pair are out of the way there. And then we've got all these. Okay. Okay, well, we have one more equatorial region left. So I can pull that off. And I can add on a lone pair there. So now what do you think we have left? Our 1, 2, 3 atoms are now in a straight line. Okay, so this is our last one we can do with our 5 electron groups. Okay, so 2 plus 3, so 2 bonding, 3 lone pair, gives me 5. All right, so I have 3 atoms this time. And 3 lone pairs. Okay, and so still 5 groups, so this is still my orbital. And this is my molecular. So the shape now, that molecular geometry, is linear. It's a straight line. with lone pairs all around that equatorial region. Okay? And so what's our bond angle on a straight line? (90 degrees). Okay, so our bond angle here is 90 degrees. All right, so some examples. Okay, I'll do that triiodide ion. And then it's a -1 formal charge on that central iodine. Okay? All right, so once again, how do we represent this three-dimensionally? Okay, so here is that xenon difluoride. So I'm going to put my fluorines like that. I have one lone pair here, one lone pair here, and one lone pair there going back behind. Okay, all right. And that concludes what we can do with our trigonal bipyramidal. I'm going to pull these off because I'm going to need them for octahedral. All right, octahedral is our last one, our 6 electron groups. This one's fairly simple. There's not as many things we can do. So in this case, we're not going to go all the way down to just 3 atoms. You notice here that I only have 3 different subsets that are going to fall under our 6 electron groups. I've got no lone pairs, so 6 plus 0 is going to give me 6. I have 1 lone pair. 5 plus 1 still gives me 6. And I have 2 lone pairs. 4 plus 2. Also, coincidentally enough, gives me 6. All right. So this is what our octahedral looks like. Okay, so 6 groups, but it's octahedral. So where is that octa coming from? Because octa means 8. Well, if I look at this, I will have 1, 2, 3, 4 faces on the top and 1, 2, 3, 4 faces on the bottom. What is 4 plus 4? 8. So octahedral comes from not how many groups are bonded to it, by the fact that it makes an octahedron with 8 different faces. Okay? All right, so we start off, as usual, for the last time, with everything bonding. 6 bonding, no lone pairs, gives me 6. Okay? So here, if I have a central atom and I have 6 surrounding atoms, we have 7 total atoms we have to account for. There's no E's, so we have no lone pairs. Okay, as usual, when everything is bonding, we have idealized geometry. And so our orbital geometry and our molecular geometry are both the same, and they're both octahedral. Okay, our bond angles here (90 degrees). Okay, doesn't matter axial or equatorial. The octahedron has perfect symmetry around it. Okay, if I take this and I toss it up in the air and I catch it in my hand, do we even know where I started with? No. It's indistinguishable. Okay, perfect symmetry. No difference between axial and equatorial. Okay, so some examples. Okay, so we'll do that second one. When we break this down and we think about, what's going to be our central atom? The iodine, the oxygen, or the fluorine? Couple of things. Definitely not fluorine. Fluorine's a surrounding atom. And fluorine's in period 2. We cannot get 6 groups around it. Oxygen, also period 2. Oxygen cannot go beyond the octet. So the only one we're left with is iodine. Iodine is our central atom. Okay. All right. Put some lone pairs on. Okay, we can do that, and we can get a negative and a positive there. Could I potentially draw something else? You be the judge. Tell me if this makes sense. Do I need any formal charges on that one? Let's hear. Oxygen 6 minus 4 plus 2 gives me 0. Iodine 7 minus 1/2 of 2, 4, 6, 8, 10, 12, 14. What's half of 14? 7. What's 7 minus 7? 0. So what do you think? Which is the better structure? They both have the same geometry though, right? Because that oxygen, if I drew it like this, there's that sigma bond. Oh, and there's that pi bond. And when we're talking about the groups around it, well, oxygen is still just one atom around it because every atom to atom connection, we have one sigma bond. So is that still going to be octahedral geometry? Absolutely. Okay. So again, this is based off an octahedron. And so you can see in the center of that octahedron would be where our central atom is. And there are 8 faces, therefore octahedral. Okay. So our side view and our top view. Does it look any different? Not really. Okay. And so we can take this. And how do we show this 3-dimensionally? Well, what we're going to do here, this one's a little bit weird. It's really hard to show this, and this in the plane because this would be sticking straight out. This is sticking straight out. That's off to the side. So these would be in the plane, but then how would we on paper show that this is sticking straight at us and this is sticking straight there? So I'm going to rotate this ever so slightly so that I have this X in the center instead. And that's how I'm going to draw it, with 2 coming out and 2 going behind. Okay? So there's one coming out, there's another one coming out, behind, behind. All right, so that's how on paper we can represent the 3 dimensions. Okay, all right. All right, let's have a lone pair. All right, so 5 bonding, 1 lone pair, still gives me 6. All right, so here I have a central and 5 surrounding, so I have 6 atoms, 1 lone pair. All right, still 6 total groups around my central atom, so my orbital geometry, still octahedral, but now my molecular geometry, that shape my molecule takes on, is square pyramidal. Okay, so you can think of this as a 1, 2, 3, 4, there's my square, pyramid. So it's a square pyramid. Okay. Now here's the thing. You might think that this lone pair is going to squish these and affect the bond angle like it has every single other time. But guess what? This is in the way. And there's 4 of these things there. There's a lot of steric hindrance here. So this lone pair actually doesn't squish up on these really. This stays a 90-degree bond angle. Okay, so this is the only time those lone pairs really aren't going to do anything. Okay, examples. Okay. All right. I'll do the xenon one. Okay. All right. Okay, so we've got a structure there. All right, now let's, I'm missing electrons. I just realized that. It's been a very long day and I can hear my 4-year-old in the background. So I'm trying to finish this one up. I'm sorry. Okay. All right. So now if I look here and I try to show this again in 3 dimensions. Back. Okay. To show that square pyramid, okay, I can put that there. I can put that there. And that there. Okay. Okay. All right. So now for our very last one, again, remember, we're trying to minimize repulsions. So where do you think is the best place? We have it like this. Where do you think is the best place to put a lone pair? Is it going to be here? Is this going to be a place of minimal repulsions? Well, no. There's going to be a lot of repulsions here. But what if I put my lone pair here? So on octahedral, this is the only time it matters where we put that lone pair. So it's going to go across from each other. So now we're going to get a flat square. And this is also why we stop here with our octahedral. This is our last consideration on octahedral, because anything else, if I try to take this off and put a lone pair here, now I've got a huge grouping of lone pairs here with a lot of repulsions, and that's just not stable. So voila, we get this. Okay. All right, so almost done here. 4 bonding, 2 lone pairs, total of 6 still. I have a central and 4 surrounding, so I have 5 atoms, 2 lone pairs. Okay. And so my orbital geometry is still octahedral because I still have 6 groups, and my molecular geometry, that shape, is square planar. All right, so my bond angle is 90 degrees, okay? So there is my molecule. All right, and so then again, when we look at it in 3 dimensions, all right, to try to put it on the paper so that we can visualize even on a flat piece of paper, we're going to do that. That, and that. And so there's our square. Okay, so that's the end of all of our geometries. You've survived all the different molecular geometries, at least the ones that we know about. Who knows? Maybe you'll go into research and you'll discover a 6th molecular shape that nobody knows about. So there's our summary for our 6 electron groups. All right, so we have one more video that I have in the molecular shape series where we're going to summarize everything into some easy to study from grids and then try a few example problems. All right, so that's coming up next.